this lecture I'm going to continue the superposition of these flows, these two cases exclusively in this class. Okay, uniform flow along y direction, which you will get when alpha equal to pi by 2. So doublet is something different from source and sink pair. Okay, if you see, this curve is plotted with reference to p infinity. Okay, that's why these points are zeros. Okay, magnitude of velocity is actually 0, and this implies ur is equal to 0 and u theta is also equal to 0 in this case. Now this is the fourth lecture of this module, potential flows anyhow, and basically in this lecture I'm going to continue the superposition of these flows. We are going to look at two important cases. One is flow past a stationary cylinder. So there is some flow past a stationary cylinder. So let us suppose if there is some cylinder and if there is some flow on it, then how we deal with the force, we will see that. And flow past a rotating cylinder. Okay, so whenever the cylinder is rotating, then how come we experience the flow? Okay, so what are the effects of the flow whenever the flow is passing over a cylinder which is rotating? Normally you see that in the case of aeroplane engines and all. So normally in air, these airplane engines, they actually go under some rotations. The turboprops and all, they actually go under some rotation. So whenever the cylinder is rotating, okay, normally you see the blades of the compressor keep on rotating and air actually passes over them. Then what happens? Okay, so we will deal these two cases exclusively in this class. Okay, and this revision, if you talk about a bit of revision, we have talked about the complex potential function f of z for any type of basic flow in general. Okay, so in basic flows we have talked about basic flows. Okay, so when we talked about this basic flows, then the first thing that we talked about is uniform flow at inclined at x-axis. I'm giving you direct expressions this time. Uniform flow inclined at alpha, uniform flow inclined at alpha to x-axis. Okay, so uniform flow inclined at angle alpha to x-axis. So in this case we have seen the complex potential function f of z is equal to u into e power minus I alpha times of z. Okay, and at all these locations z is a complex number in a complex plane, x plus iy, which can be also written as r into e power I theta. Okay, in modulus amplitude form we have seen this. Okay, u into e power minus I alpha times z. Now once this is done, we talked about concept of source. So source of strength m, placed at z naught, placed at z is equal to z naught. So in this case we have seen the complex potential function in this case turns out to be f of z is equal to m by 2 pi log z minus z naught to the base e. Correct, we have seen this log z minus z naught to the base e, and then we have seen this case of sink. If you have sink, then definitely there is a minus sign here, that's it. Okay, we have seen basically in case of sink the velocity is in the negative direction of radius, so in the decreasing direction of radius, so there comes a minus sign here in case of sink. Okay, and we have seen that in case of a doublet, or generally first of all in case of a vortex flow, vortex of circulation, basically strength of the vortex is measured in its circulation gamma. Actually we have seen circulation gamma in this case placed at z is equal to z naught. Okay, so placed at z is equal to z naught. If you see in this case we got the complex function as f of z is equal to minus I times of circulation by 2 pi times log z minus z naught to the base e. Correct, so this is what we got, log z minus z naught to the base e. Okay, so this is what we got, and then we have talked about the case of a doublet. Okay, so what is a doublet? So now when we talked about doublet is the combination of source and sink which are placed very close to each other, and these two strengths of source and sink are assumed to be equal. Correct, so here if you see we have seen that in this case doublet is basically the combination of source and sink of equal strength, source and sink of equal strength that are placed close to each other, that are placed very close to each other, that are placed close to each other, that are placed close to each other. So in that case we have seen the complex potential function f of z is equal to f of z is equal to c by z, where c is some constant. Okay, c is some constant, so c by z. Okay, so this is what we have. So these are the main things that we looked at, and of course many other things like uniform flow along x direction, which you will get when you put alpha equal to 0 in this equation. Uniform flow along y direction, which you will get when alpha equal to pi by 2. Then uniform flow inclined at x axis. Okay, then we have seen the concept of source, what is strength of the source. So source and sink concepts we have seen, and then after we have seen the concepts of doublet actually. So doublet is something different from source and sink pair. Okay, source and sink pair can be any source and any sink of different strengths placed at some different locations, but doublet is one special combination of source and sink pair whenever source and sink are of equal strength and they are placed very close to each other. Okay, so that we have talked. And vertex of circulation, say circulation gamma placed at some z is equal to z0 is identified as this particular function. In yesterday's class I have shown you all these cases. Okay, and in yesterday's session we have also talked about superposition of flows. So firstly we superimposed these two flows, means basically uniform flow in x direction and this what do you say, source of strength m placed at some location. Okay, so we have seen there is some half body which got developed actually. Okay, that's called the Rankine half body, and in that Rankine half body we talked about this. In the Rankine half body we talked about what is the width of the Rankine half body, what is the stagnation point. In Rankine, in the case of flow over this half body, Rankine half body, when you equated total velocity is equal to 0, means when you equated f dash of z to 0, how many stagnation points? Only one stagnation point, correct? And that stagnation point is also at a radius of m by 2 pi u, and of course in terms of complex numbers z is equal to minus m by 2 pi u. Okay, so that's what we have seen. So in today's session we will go forward and we will try to look at superposition of some other flows actually. Okay, so the first case, superposition of a uniform flow, superposition of a uniform flow and a doublet actually. Okay, and a doublet. This is one very important case actually here, superposition of a uniform flow and a doublet. Okay, so we'll see how this is, why this is called, why this can be seen as a situation of flow past a stationary cylinder. Okay, like in yesterday's case I have told you why we can treat the superposition of uniform flow and a source as flow over a Rankine half body, because there exists one particular streamline such that practically there cannot be any flow into that particular streamline. So this streamline acts as some solid, this can be assumed as some solid body, so that the flow over this body can be assumed as, means that if you look at the streamline equations and all, you can understand the flow in that particular situation of uniform flow plus source is equal to flow over a Rankine half body. Okay, now similarly here in this case, superposition of a uniform flow and a doublet. Okay, so first of all uniform flow plus doublet. Okay, so we have seen in case of uniform flow we have this streamlines along the flow direction basically. So if you see this streamlines along the flow direction, I'm talking about only means there is some flow in one direction, so that's why I have taken along the x direction. Okay, so there is some flow along this, so this is at a free stream velocity of u plus. Now in case of doublet we have seen, in case of doublet if you see we have done the streamlines and the equipotential lines. So the case of doublet will be something like, the streamlines are something like this. So the streamlines are tangential to this x axis. So streamlines are actually tangential to x axis. So let me draw carefully. Similarly, if you draw things like this, so these are basically the streamlines. Normally you have the, these are in anti-clockwise sense of course normally, and this is in clockwise sense, because you see what happens in the x direction and y directions depending upon the this velocity what we got, f dash of z u minus I, u r minus I times of u theta. Now in the increasing direction of in the decreasing direction of like this, if you take for example these are the actual streamlines. Okay, and equipotential lines we have seen. Equipotential lines, if you try to draw, okay, fine, let us draw the streamlines only, because let us not make the diagram much complicated. Okay, U plus a doublet. Okay, so we have a doublet also here. So source, this is basically the case of a doublet. So when you superimpose these two flows, what is the resulting flow? That's what we are interested in. Okay, so first we'll start with the complex potential function for any case, like for superposition of uniform flow and doublet, for superposition of uniform flow and doublet, for superposition of uniform flow and doublet, let us see what comes out. F of Z is equal to, so uniform flow, the complex potential function for the uniform flow is uz, plus for the doublet we have seen this is C by Z, correct? So this is C by Z for the doublet. Okay, now here I'm just making one small modification, that let this C, whatever is there, is equal to some U into A square, for example. Okay, so we can write the C as some product of U into, because this I want this as U into some constant square. A is some constant actually, so this C can be written as U times of A square actually here. Okay, so when you write that, this expression, because this is just a constant, correct? So this constant can be written as U into A square. Normally this constant is nothing but M into epsilon. If you see the yesterday's class, source of strength or sink, strength of a source or sink into this epsilon. So that M into epsilon we have written as C into pi, like that. Okay, so C is some constant which can be adjusted, so that C I'm writing as U into A square. Then this implies your F of Z becomes U times of Z, because this is for the uniform flow, plus U times A square by Z. This is the total complex potential function. Okay, now if you want velocities in this case, then let us see F dash of Z is equal to, or first of all, if you want stream function and equipotential, this potential function, if you see U into R e power I theta plus U A square by Z, this gives U A square by R into e power minus I theta, correct? Because here if you write Z as R into e power I theta, R is as it is, this e power I theta in the denominator can be written as e power minus I theta onto the numerator. So now if you expand this using cos theta and sin theta expansions, U R times of cos theta plus I sin theta plus U A square by R times of cos theta minus I sin theta. Okay, so this, if you segregate to real parts and imaginary parts, we get U R cos theta plus U A square by R cos theta. So this is the real part, plus I times of imaginary part, U capital R times sin theta minus U A square by R times sin theta, correct? So if you take cos theta and sin theta common from both the terms, just for simple things, so U R plus U A square by R times of cos theta plus I times of U R. If you take out, then we have sin theta minus sin theta minus. Okay, so if you take U R out again, instead of that, we'll take only sin theta term. So U R minus U A square by small r times of sin theta, correct? So this is what you have, you are able to do by splitting into real part plus imaginary part. So this real part is nothing but velocity potential function in terms of polar coordinates, and this imaginary part is nothing but the stream function, correct? Because initially we know that F of Z is equal to phi plus I times of psi. So if you split this, then we got the velocity potential function in terms of r comma theta as this phi of r comma theta, and this in case of stream function, we got this stream function as U R minus U A square by R times of sin theta. So let us write here this thing. So we got something like phi of R comma theta is equal to U R plus U A square by small r times cos theta, and psi R comma theta is equal to U R minus U A square by small r times of sin theta. So this is equipotential function and this is the stream function actually. Okay, so these things has to be identified, because you see many times they give you these expressions, they are of this actually. Okay, so these two normally in fluid differential analysis of fluid systems and all, whenever they're talking about velocity potentials and stream functions, they will give you these expressions. These expressions are nothing but the expressions of this case where there is superposition of uniform flow and a doublet. Okay, so but anyhow, when they give you these functions, just treat them, they are the phi and psi functions. Okay, now let us calculate the velocity. Okay, so f dash of z, considering f dash of z, considering f dash of z actually, which is equal to ur minus I times of u theta into e power minus I theta. Correct? We have seen this, how this expression comes out. F dash of z will be equal to ur minus I times of u theta into e power minus I theta. Now observe carefully one thing. F of z is equal to uz plus ua square by z. So if you differentiate this, f dash of z is equal to capital U plus u into a square into derivative of 1 by z is minus 1 by z square is what you have here. Okay, so this is minus 1 by z square. So now if you split this, u minus u a square by z square. Now how do I write this z square? You know, z square is equal to r square into e power minus I theta. Correct? So this can be written as u minus u a square by r square into e power minus I times of 2 theta is what you can write here. Okay, into, because this z square can be written as r square into e power I 2 theta. So this e power minus I 2 theta I have written here. But since I want something in this form, let us do one thing. If I want to write this something as some quantity into e power minus I theta, that I can write it as, look, u minus u a square by r square something into e power minus I theta. Then here one e power I theta should come here because there is only one here, there is no exponential terms. If I want to take e power minus I theta common, I should write only e power I theta. Then if I want to write e power minus I theta common, out of this e power minus I theta there will be only e power I theta, just adjustment of some complex numbers. Is this clear till this point? How I have adjusted this e power minus I theta actually? Because I want something in this form, because this is the standard form that we have taken out. So that if you take e power minus I theta term common, then we have adjusted one e power I theta into the bracketed terms. That's it. Okay, clear? Now is it clear? I hope you don't have any doubts till this point. Okay, very simple mathematical conversion. That's it. Okay, some plus 10 plus 1 plus 2 kind of things that I'm doing in complex numbers. So if you expand this, now this implies f dash of z is equal to u times of e power I theta. So if you expand that, u times of cos theta plus I sin theta minus u a square by small r square times of cos theta minus I sin theta. So this total multiplied with e power minus I theta. Okay, so this if you simplify, f dash of z is equal to, now take the real parts actually. So if you take the real part, u cos theta minus u a square by r square cos theta. Okay, so u cos theta plus u cos theta minus u a square by r square cos theta. So this is the real part. Okay, this is the real part plus I times of u sin theta minus of minus plus u a square by r square times sin theta. So this total value multiplied with e power minus I theta. Now since you want this minus sign here, what we'll do, we will adjust one minus sign all over. Okay, so because you want a minus sign here, so therefore f dash of z is equal to from these two terms, if you take cos theta common, we have u times u minus u a square by r square times cos theta is what you have, for example, minus, because if you take minus, I times of minus u a square by r square sin theta. Okay, so this term multiplied with sin theta, this whole value multiplied with e power minus I theta. Okay, so that e power minus I theta comes out. So if you see, then this is your radial component of velocity and this is your theta component of velocity at any point in the flow. Therefore ur is equal to, radial velocity is equal to u minus u a square by r square times of cos theta, and u theta is equal to minus u minus a square, u a square by r square times of sin theta is what you have here. Okay, so this is minus u a square by small r square sine theta. So these are the radial and theta component velocities here. Okay, now if you write them, therefore ur is equal to, so ur is equal to, if you take u out from the total term, u times of 1 minus a square by r square times cos theta, and u theta is equal to minus u if you take out, minus u if you take out 1 plus a square by r square times of sine theta. Correct? So these are the terms of velocity at any given location. Clear? Okay, now very simple analysis. Okay, nothing big, but the terms look bigger, but actually they are very simple to do. Just write this e power I theta as cos theta plus I sin theta, cos theta minus I sin theta, then grouping the terms. That's it. Okay, they are looking lengthy, but actually the things that are involved here mathematically is very simple to do. Okay, now if you see, this is what you have. These are the radial and theta component velocities, and if you take the velocity potential function and the stream function, these values are also, let us summarize this. Okay, because our main point of interest is these four things: u r, u theta, phi and psi. Okay, for that you have done some mathematical analysis here. So phi is u if you take out r plus a square by r cos theta, u if you take out then r plus a square by small r cos theta, and what about psi here? So psi is u times r minus a square by r, u times small r minus a square by r times sine theta. Correct? So this is sine theta. Okay, so we have this thing. So these are the four things which are important. So this is the function that we have seen. So if you differentiate this with respect to z, u into derivative of z is 1 plus u a square into derivative of 1 by z is minus 1 by z square. Okay, so then u minus u a square by z square is what you have. So z is equal to r into e power I theta, so z square will be r square into e power I2 theta. Okay, so I have sent this e power I2 theta to the numerator with a minus sign here. Now what we have done is, since this is the standard form for writing radial velocity and azimuthal velocity, means the velocity in the theta direction, I have tried to convert this equation in form of this actually. Okay, so for that I need one e power minus I theta. Correct? So what we have done is, we have taken one e power minus I theta common from these two terms. Okay, when I take e power minus I theta common from these two terms, we will get an e power I theta, so that when you multiply the first term with this, you will get u again. E power I theta into e power minus I theta, they get cancelled, minus u a square by r square into this e power minus I2 theta I have taken as e power minus I theta into e power this minus I theta basically. Okay, so when I try to take e power minus I theta common from these two terms, this is the expression which is left over. Okay, now we have written this e power I theta as cos theta plus I sin theta, e power minus I theta as cos theta minus I sin theta, and you have multiplied. So when you multiply u into cos theta, u cos theta, minus u a square by r square into cos theta. So these two terms are the real terms in this. Okay, and these two terms are the imaginary terms. Okay, so we have written the things in terms of real part minus I times of imaginary part. That's it. Okay, so when you do this, there is no minus sign here, but since you want a minus sign here before I, so to keep a minus sign before I, these two terms are made negative with a minus signs. Okay, so that's how we got these expressions, and these are the expressions for which we have. Clear? Now let us see, if we know along a streamline, psi is equal to constant. Psi is equal to constant. So if, for example, if you take this expression, psi is equal to 0, means psi is equal to 0 actually. Okay, so what's the meaning of psi is equal to 0 physically? There is no value of the stream function, so definitely there is no velocity of the particles in that particular streamline. Okay, so therefore if you see, if psi is equal to 0, this implies u times of small r minus a square by r is into sine theta is equal to 0. But actually if you see, sine theta is 0 only at some finite number of points actually, means at theta equal to 0, theta equal to pi, theta equal to 2 pi, such kind of only some 2-3 number of finite number of points, this stream function is 0. But independent of theta, at any location, if psi has to be 0, this implies small r minus a square by small r, this quantity has to be 0. Okay, because if you see, this sine theta equal to 0 gives you only some finite number of points, but irrespective of the orientation, at any given point, if this stream function has to be 0, then this quantity has to be 0. And what does this quantity gives you? This implies your r is equal to a actually here. So small r is equal to a, correct? For this equation to be 0, r square minus a square has to be 0. So small r is equal to, r is actually some length, so I am taking only positive value, r is equal to a. What is the geometry of this curve? Radius is equal to some constant value, so radius is fixed. So in polar coordinates, if you put radius is equal to some fixed quantity, then this curve denotes what is the geometry of this curve here. So r is equal to a is what you have. Circle, correct? Because it's a circle, right? Because if you see small r, if you square both sides, we'll have r square is equal to a square. So what is r square? X square plus y square is equal to a square. That's it. Okay, so this is actually some equation of a circle actually. Okay, so this is circle of radius a. This is circle of radius a. Now try to understand one thing. So one streamline is actually something like this. Okay, so streamline is something like this. This is a streamline, r is equal to a. It's a closed streamline. Then in such case, whenever this is the streamline which is denoting a circle actually, then practically flow cannot enter the streamline. Okay, there cannot be any flow across the streamlines. Okay, means can I say, and of course there can be some flow inside, the inside flow cannot actually come out also. So can I say that if I take the flow in this condition, since flow cannot practically enter this, whatever the flow is coming, that should travel only on the outside, it cannot enter inside. So for in the third dimension z also, if you take, we have done this analysis only in xy plane. Okay, so for example, if you take the third dimension z, then can I say there is actually this situation, flow around this particular streamline can be taken as flow past a cylinder, because practically this streamline acts as a solid surface because flow cannot enter this. So that's why this, if you take in the z dimension also, this I can assume as a cylinder of some length L for example, then this situation can be talked as flow past a cylinder, because in the z direction if I take at any location of z, analysis will remain same in the xy plane. So that's why this case can be identified as flow past a cylinder. Okay, so flow past a stationary cylinder, because here if you see, this is the velocity of the particles here is 0. Okay, so whenever the velocity of the particles here is 0, then definitely this cylinder is a fixed cylinder actually. Okay, now if you take the flow on this, means if you dot different streamlines again for psi equal to 1, 2, 3, all these things, then the curve that we get here is, in this case is equal to something like this. So this is psi is equal to 0. Then for some other flows, okay, so this is how we get the streamlines, other streamlines if you plot. Okay, so if you plot the other streamlines, we get psi is equal to c1, psi equal to c2, psi equal to c3. Okay, psi is equal to c4, like this. You get different streamlines like this. Okay, so that's basically, if you plot this, you will get that shape. For example, if you want me to show, I can show you actually, but I think I have to solve the quadratic equation. Okay, fine. So for this time, let's try to see this. Normally if there's some MATLAB or something, I would have plotted easily, but using the conventional plotters it is slightly difficult. Okay, so right now if you see, psi is equal to c1, c2, c3, c4. So like this, how we have the streamlines, and one particular streamline for one value of psi is actually a circle. Okay, so that's why practically flow cannot enter this circle. So that's why this is taken as the case of flow. This in the third dimension, if you take the length also, then this can be assumed as a cylinder, and this story can be talked as flow past a stationary cylinder actually. Okay, now if you see a few more things, look, I want to talk about some things here. So here if you see one thing, at any points on the surface of the cylinder, if you say at r is equal to a, what is the meaning of r is equal to a? So this is origin, for example, this is the origin in the complete system. So if at origin, if you see at r is equal to a, ur is always 0, because irrespective of theta, at r is equal to a, for any value of theta, we have ur is always 0. Yes or no? Because here if you see, this is the expression for ur, whatever the value you put in place of theta, as long as this a is equal to r, this term will go to 0. That's why this radial velocity is 0. Practically what does this mean? Look, if you take flow at any point at a radius r, means basically all these points will come on the surface of the cylinder. at any point flow cannot try to come towards the radius. Okay, this coming of flow towards the radius cannot happen. Okay, so the particles cannot have any radial velocity. Okay, because if you are taking r equal to a, points will come, the points in the flow will come on the top of this particular streamline, means basically on the top of this cylinder. So at any point on the cylinder, flow cannot actually enter towards the radius. That's why if you see, flow cannot have any radial velocity at any given location. Okay, so this is theta equal to 0 normally, then theta equal to 90, 180, 270, again 360, 30, 120, whatever you take at any location, you cannot actually have some what do you say, you cannot actually so basically if you take this as the reference so that you can understand, so this is the actual reference plane. So your r and theta are measured according to this. Okay, so r and theta, for example in this case, then at theta equal to 0, 90, 180, at any location you cannot have any radial velocity. Okay, now what about u theta? At r is equal to a, u theta is equal to, at r is equal to a, u theta is equal to, so if you keep r is equal to a here, capital U times of 1 plus a square by r square. Okay, so capital U times of, I think minus sign is also there, so minus u times of 1 plus r square by small r square into this sine theta. Okay, so we have a sine theta here. Just a minute, who is calling? Okay, is everything fine, audio and video? Because normally people call technical side when there is some issue. Is everything fine? Audio and video both are fine, right? I hope there is no issue. Yeah, okay, good. So let's continue. So here if you see, this small r square by small r square is actually 1, so that's why 1 plus 1 gives you 2, so u theta is equal to minus 2 times of u sine theta at any given location. Okay, so at any point in the flow, this u theta has this velocity, means basically all these particles which are just outside the flow, they have certain velocities which are equal to this minus 2 times of u sine theta. Now I want to tell about one thing. First, stagnation points. Okay, so first stagnation points, if you want to identify where are the stagnation points in this case, means the points where the localized flow is actually 0. So if you talk about the stagnation points, you know, stagnation points are those points at which magnitude of velocity is equal to 0. This implies I is equal to u r is equal to 0 and u theta is equal to 0. So tell me, when r is equal to a, when r is equal to a, u r is anyhow 0, and for u theta is equal to 0, this implies, yes, so see, at r is equal to a on the surface of the cylinder, for this u theta to be 0, then sine theta should be 0, which means theta is equal to 0 or theta equal to pi. These are the two possible locations where you can have 0 velocity in the azimuthal direction, means u theta is 0, and whenever the points are on the cylinder, definitely u r is 0 at any location. So that means here we have chance of 2 stagnation points, one stagnation point at this location, radius equal to a and theta equal to 0, another stagnation point, radius equal to a and theta is equal to pi actually here. Okay, so if you try to plot those stagnation points, for example here, so for example this is the circle r equal to a, and this is, okay, and this is for example say the actual reference system, then this is the origin, this is theta equal to 0 anyhow. Okay, so theta equal to 0. Now if you see the flow past this, the flow comes like this and you know it escapes like this. Similarly it comes and fine. Okay, so this is how you have the flow, for example, for different streamlines. Okay, for different streamlines. Okay, so there is some flow over this cylinder. Now try to understand one thing. If you see So try to get this point. So this is what you have here. So theta is equal to 0. Okay. Now if you see, the location of r is equal to a and theta equal to 0 is here, just in front of this. Actually this is the point, so slightly before that the fluid comes to rest. Okay. Similarly, theta is equal to r equal to a and theta equal to pi is this point. Okay. So therefore you have two stagnation points in this case. So the fluid will try to come here, then its velocity gets reduced almost to 0, and then it actually diverts into two different paths actually. Okay. So these are the two locations where the fluid is completely at rest, and these 2 points are the stagnation points in this particular case. And this stagnation point which is here is called forward stagnation point. Forward stagnation point, because normally this is the flow direction if you take. So forward stagnation point, and this point here is rear stagnation point. Stagnation point. Okay, so this is a rear stagnation point. Clear? So we have two stagnation points in this case. One is the forward stagnation point and another value is the rear stagnation point. So this is very important thing here. Okay, so this is a rear stagnation point. Now I want to do one analysis here, because I promised you one thing. When I'm talking about the concepts of drag and lift, I told you there is something called wake region, which I'll discuss in the potential flow. This is what I have told you actually. Okay, so let us see. Normally this region which is here is called wake region. Okay, so this region which is here generally, so this region which is here, this region which is here generally is called wake region. Okay, so this is called wake region. So what is the meaning of wake region? Look, I'll tell you. See here, if you try to do some analysis here, okay, so there is one concept which is called coefficient of pressure. Coefficient of pressure actually. Coefficient of pressure. So what is the case of this coefficient of pressure? Look, let us talk about. See, let us suppose you take 2 points in the flow, for example. Let us suppose you take 2 points within the flow, something like this. Okay, so you take 2 points in the flow such that one point is on the surface of the cylinder and one point at some large distance away from this. Okay, so these 2 points I'm considering. So if you see carefully, I'm considering 2 points, these 2 points, such that these 2 points are horizontally on the same level, but one point is on the surface of the cylinder. This is point S, for example, and this is point 1, for example. Let us say, okay, one is when the flow didn't get disturbed because of the presence of this cylinder. Okay, the flow is smooth at that location. Now if you see one thing, since this flow is inviscid, I can apply Bernoulli's equation, and since this flow is irrotational, I can apply between any 2 points in the flow. Okay, so therefore we have seen, do you all remember in case of vortex flows and all, I have told you if the flow is irrotational, you can apply Bernoulli's equation at any 2 points in the flow, but if the flow is rotational, you can apply the Bernoulli's equation only on the same streamline. Yes or no? Did you remember this point? This point is very, very important. I have told you this, and we have done some mathematical understanding there. Clear? So can you remember this point? So can you recollect this point that we have discussed this? In a irrotational flow, you can apply Bernoulli's equation at any 2 points in the flow, but in case of rotational flows, you can apply only on the same streamline. Correct? We have talked about this. Now if you see, since this flow is irrotational, because potential flows are ideal flows, they are irrotational flows, we can apply Bernoulli's equation at any 2 points in the flow. So I have applied this Bernoulli's equation basically at these 2 points, 1 and S. My intention is to tell you that these points are such that one is at very far distance, such that there is no disturbance of the flow. The flow is coming with some phase stream velocity, and here at this location, if you see, that point is on the surface of the cylinder. Okay, now if you mean slightly just before the surface of the cylinder. Okay, and these 2 points are horizontally on the same level. So applying Bernoulli's equation. So first of all, what is this coefficient of pressure? Let us see. So P infinity minus P theta by half rho u square, u infinity square. Okay, so this is what you have for the coefficient of pressure, Cp actually, where P infinity is the pressure of fluid at free stream conditions, actually. So at free stream conditions, and P theta, generally it's called PS, P theta is PS, which is pressure of fluid at a point on the surface of the cylinder. Pressure of fluid at a point on surface of the cylinder. At a point on surface of the cylinder. Okay, so at the point on the surface of the cylinder. Clear? And u infinity is again the free stream velocity of the fluid much before the cylinder. Okay, so this is called coefficient of pressure. So to calculate this coefficient of pressure expression, let us do some analysis. Okay, so here applying Bernoulli's equation, applying Bernoulli's equation between the points 1 and S, between the points 1 and S, what we have taken here. Okay, so between the points 1 and S. So at location 1, since the conditions are free stream at this point, so we can write this implies P infinity by rho z plus u infinity square by 2z plus z1, okay, is equal to P theta or PS on the surface of the cylinder by rho z plus v theta or u theta square, because on the surface of the cylinder we have only u theta, we don't have any radial velocity, so velocity is only equal to the u theta, so that's why v square is nothing but u theta square. Okay, so divided by 2z plus zs. Okay, now if you see these 2 points intentionally have taken on the same horizontal reference, so this z gets cancelled. Okay, now from this equation, of course if you can cancel g all over from the remaining terms, then you understand one thing, that P infinity minus PS or P theta. P theta is same as PS, that's what I mean actually. So P theta is pressure at any angle theta or generally on the surface of the cylinder at any point. Okay, so P infinity minus PS by rho. P infinity minus PS by rho is equal to half times of u theta square minus u infinity square, correct? So half times of u theta square minus u infinity square, which is actually the u square at the free stream conditions. Okay, in our case u infinity is capital U. Okay, because we have taken free stream velocity is capital U. Okay, so this is the case. Now if you try to take this rho u infinity square, actually this half if you bring here, and if you try to take u infinity square outside, okay, u infinity square to the bottom, so P infinity minus PS is equal to u theta square minus u infinity square divided by this value actually, right? So PS or P theta minus P infinity, let us shift this, P theta minus P infinity, P theta minus P infinity. Okay, so let us write this equation. So PS minus P infinity in this case is equal to, or let us keep this, P infinity minus PS by rho is what you have here. Okay, now this coefficient, please change this. This is P theta minus P infinity. Okay, it's not P infinity minus P theta, just change this, P theta minus P infinity. Okay, now if you see P infinity minus PS by rho is given by this equation, half times of u infinity u theta square minus u infinity square. Therefore PS minus P infinity by half if you bring to the bottom, half if you bring to the bottom, and if you take over here, this is equal to, since you swapped these two terms should also be swapped actually. Okay, so u infinity square minus u theta square. So PS minus P infinity by half rho. From these two terms, if you take u infinity common, okay, u infinity square if you take out, this becomes 1 minus u theta by u infinity whole square. Okay, so this is the expression for the coefficient of pressure. Okay, so therefore PS minus P infinity by half rho u infinity square is equal to 1 minus, is equal to Cp, of course coefficient of pressure, which is 1 minus u theta or 1 minus u theta by u infinity whole square. Okay, so this is the case for the coefficient of pressure. This is the case of coefficient of pressure. Now if this is the case of coefficient of pressure, then try to understand one thing. If you take the cylinder, for example, look, if you have some value of P infinity, for example, if you take P infinity as the reference value, if you take that as 0, for example, then in such case, what is the variation of pressure on this particular case here? If you see this, look, for the cylinder or for the flow here at r equal to a, because you are talking on the surface of the cylinders at important, u theta by u. Okay, because you see u theta by u infinity is equal to, what is the expression for u theta actually? U theta is how much? U theta is minus 2u sin theta. At any point on the radius, u theta is given by minus 2u sin theta. So minus 2u sin theta by, what is the value of u infinity? We have taken the phase time velocity as u actually. Okay, so this if you plot, u gets cancelled. Therefore, pressure coefficient, which is p theta or generally p surface minus p infinity by half rho u infinity square. Half rho u infinity square is equal to 1 minus u theta by u infinity whole square, which is 4 times of sine square theta. 4 times of sine square theta actually here. Okay, so this is 4 times of sine square theta. Correct? So this is what you get. 4 times of. So this expression is 1 minus 4 times of sine square theta is the coefficient of pressure. This expression actually gives you one thing. Look, try to understand carefully. P infinity is constant at some far location where the flow is coming with some pressure, so that's constant value. Half rho u infinity square is also constant value. So one thing you can observe, the variation of pressure means Ps actually. Okay, so if you see, Ps is equal to P infinity. So this if you multiply here, so plus half rho u infinity square times of 1 minus 4 sine square theta. So this is the expression for pressure at any location in the flow. At any location in the flow, correct? So at any location on the top of the cylinder, if you want to talk about the pressure acting on the surface, this pressure acting on the surface is given by this particular expression and it depends on the theta value. Clear till this point? Why I'm doing this, I'll tell you, because I want to show you the calculation of lift force, because at that time I've told you that it's a lengthy calculation, CL is there, but this is one special case where we can see some calculations. Okay, so yeah, Ps is equal to P infinity plus half rho u infinity square times 1 minus 4 sine square theta. Clear? Now try to understand this one thing. The points where Ps is equal to P infinity means, let us suppose what happens is, slowly look, try to understand one thing that happens here. Initially what happens, look, whenever the flow is coming, here the flow has certain velocity, but as the flow starts coming towards close to the cylinder, the velocity of the flow gets reduced, because practically you can observe there is some obstacle here, so the flow velocity keeps reducing and theta velocity actually tries to increase, correct? So when this happens is basically, if you see, when the flow is traveling in this particular direction, the pressure energy of the flow is, means the kinetic energy of the flow gets converted to pressure energy, correct? So the kinetic energy of the flow gets converted to pressure energy, but at one particular location or generally at some location, definitely. And what happens, look, whenever the flow is coming like this, velocity keep on decreases and again the velocity keeps increasing. Okay, so whenever this increasing of velocity is taking place, again the pressure energy gets converted to kinetic energy. So therefore there comes some point in the flow definitely at which this stagnation pressure, this pressure at this location 1 is same as the pressure on the top of the cylinder. So let us identify that points. So if P theta is equal to Ps is equal to P infinity, this implies Cp is equal to 0. This implies 1 minus 4 sine square theta is equal to 0 actually here. Okay, so 1 minus 4 sine square theta equal to 0. So this implies sine square theta is equal to 1 by 4. So sine theta is equal to plus or minus 1 by 2. So what are the points at sine theta equal to 1 by 2? If sine theta is equal to 1 by 2, then this implies theta is equal to 30 degrees or 150 degrees. Similarly, if sine theta is equal to minus half, okay, so if sine theta is equal to minus half, then this implies your theta is in the third quadrant, so pi plus pi by 6, which is 7 pi by 6, 7 pi by 6, or generally theta is equal to 2 pi minus pi by 6, which is 11 pi by 6 in that case. Okay, so this is 11 pi by 6. Okay, means basically if you see these 2 points, if you see these 4 locations, means theta equal to pi by 6. Okay, let me draw the curve here. So if you take this cylinder, for example, So if you take the flow like this, so if you see in this case, so this is for example center, and let's suppose the reference is this theta equal to 0 line. Now in this case, if you see at 4 points in the flow, so at 4 points in the flow, theta equal to pi by 6, theta equal to 5 pi by 6. Similarly, theta equal to 7 pi by 6 and theta equal to 11 pi by 6. At these 4 locations, the pressure of the fluid is again same as the free stream pressure. Clear? So that's why if you see these 4 points have again the velocity which is equal to u infinity actually. Okay. These are the points which are of importance here. Okay, so these are the points theta equal to pi by 6, 5 pi by 6, 7 pi by 6 and 11 pi by 6. These are the points at which the pressure on the top of the cylinder is again equal to the free stream. So the pressure is actually equal to the free stream pressure. Okay, now if you want to observe so basically these are the 4 points that are of interest, and if you want to observe the pressure distribution on the cylinder, means if you try to plot this function 1 minus 4 sine square theta, look, I will try to plot this. R is equal to 1 minus 4 sine square theta using a plotter. Polar graph plot 1 minus 4 sine square theta. I will try to plot this. So 1 minus 4 sine square theta. So see here 1 minus 4 times of, or 1 minus 4 times of sine square here theta. Okay, so this is the case. So if you plot this, you can see entire valid expression. Okay, so for 1 minus 4 sine square theta. So if you enter, so this is how you actually get the curve. Okay, so normally if you zoom it slightly, or generally if you make it small, the pressure variation will be something like this on the case. Okay, so here if you see, this is not exactly the case. So this is how the 1 minus 4 sine square theta curve will actually look like. In actual case, how it looks is, you have the pressure variation like this. This is how the pressure varies actually. Okay, means basically if you see, and between these points 5 pi by 6 and 7 pi by 6, if you plot, this is how you get the curve. Okay, so this is how you get the pressure variation on the top of the cylinder. Pressure variation on the top of the cylinder basically. So this is the pressure variation on the top of the cylinder. If you plot that, you will get this particular curve. Okay, similarly the pressure is always normal to the surface. So so 1 minus 4 sine square theta expression will be something like this. Okay, and these are something like semi-cycles actually, if you talk correctly. And the pressure is actually something like this. So I want to ask you one thing here. Looking how pressure increases and decreases because of this particular function actually. Okay, so that's what I'm trying to explain now. So if you see the pressure variation which we have calculated using this analysis, we understood that the pressure actually increases and decreases. So if you observe this region, which I'm talking as this particular region, if you talk about this region, in this particular region, so try to see what comes out here. Okay, so look, in this particular region, whenever theta is lying slightly to this, if this quantity is, for example, negative, let us suppose. Okay, so let us suppose if this quantity is negative. Okay, so if this quantity is negative quantity, if this quantity is actually negative quantity, for example, 1 minus 4 sine square theta is negative, which means theta is less than pi by 6, which is this area, and theta is less than pi by 6. Okay, 5 pi by 6. Okay, this area. Similarly, theta is less than 7 pi by 6 and 11 pi by 6. So these are the areas which are in between these two angles. Okay, in between this pi by 6 and 11 pi by 6 is this portion, means this angle of theta, which is between pi by 6 and between this pi by 6 and this 7 pi by 6, 11 pi by 6, and this is the area between this 5 pi by 6 and 7 pi by 6. Now within this region, if you see, this pressure is actually, so this quantity is actually negative in this case. Okay, so whenever this quantity is less than this, it is negative, right? So whenever theta is less than pi by 6, this value is less than 1 by 4. So this quantity is actually positive. Okay, so fine, yeah, this is positive. So whenever this is actually positive, here you can observe one thing. This is symmetric distribution, but if you see carefully here, onto the top of the cylinder, whenever this is the pressure variation, this means, let us suppose if the cylinder, let us suppose if this is air, for example, and if the cylinder is trying to move in this direction, for example. Okay, so let us suppose this is air, and if the cylinder is trying to move in this direction, like in case of golf ball and all, what happens, the ball tries to move in this direction, then in front of the flow there comes some location where the pressure acting on the ball will be in the reverse direction. Okay, so this wake region will actually, the pressure in the wake region in such a way that it actually obstructs the motion of the fluid actually. Okay, there is already drag because of this complete pressure that's acting and all. Okay, but here if you see in this particular location, since some part ahead of the motion, you have something called the wake region, and in this particular region the body actually experiences some restriction for the movement. Okay, so this is called the wake region. This block actually tries to push this ball back actually. Okay, so that's why this wake regions, on study of this wake regions, is a bit important. Okay, not at our gate level, but normally if you do research on this movement of objects and all, then in such cases this is important. Okay, but this is how the pressure actually gets converted, and there is actually increase and decrease of pressure because of this particular thing what we have done actually here. Okay, and we have clearly identified on the top of the cylinder what are the velocity components and all. So this is how it happens, and because of this wake region, some strong pressure will get developed again in this particular regions. Okay, and these are the 4 points which we have discussed here in this case. Clear? And this region is called the wake region. So in this, basically the velocity is again decreasing. Okay, so if you see, because of this minus sign, what happens, this pressure, so pressure actually, if you see, this pressure is showing some fluctuation here because of this 4 sine square theta term, and if pressure is showing some fluctuation, obviously velocities will also show certain fluctuations, because total pressure energy and kinetic energy summation should be same in that, should be a constant value. Clear? This pressure, because you clearly got the expression for pressure, is changing, and with respect to theta this quantity changes, so pressure actually changes. Okay, with theta all over. Okay, so since sin theta can increase in some 0 to pi by 2 and decrease from pi by 2 to 0, that's why pressure can also increase and decrease in this region which is around the cylinder. Clear? Now I want to ask you one thing. If you look at this combination, for example, the pressure force is in such a way that it is looking symmetric, correct? Then can you please tell me what is the lift generated on the cylinder? In this case, means the cylinder is stationary and some flow is coming. So in such case, which is this case, looking at this pressure distribution, lift that gets generated in this case, because now you came to the expression that P depends upon, okay, PS is equal to, this is the pressure variation. Okay, so will there be any lift that gets generated? No, practically there won't be any lift on a stationary cylinder. If you try to calculate, look, I will show you, the lift is actually 0. I will show you how this happens. If you take the surface of the cylinder, for example, so at one location, if you take the pressure, for example, okay, so let us suppose at some location theta, so let us suppose at some location theta, or generally theta we have measured in the anti-clockwise sense as positive. So let us do one thing. At this location, if the pressure is P, PS. Okay, so PS is the pressure at this location. Now, if this is the center origin, so this is theta, for example, theta. Now, let us suppose you take some small length of this particular cylinder. Okay, so you take some small length of this cylinder, for example, something like this, some small length. Okay, so like this. So this is R and this angle is d theta. So this length of the cylinder that I am taking is R times of d theta, is the total length, small length on the small circumference of the cylinder. Okay, now if you see, let length of the cylinder is L, for example, let length of the cylinder is L, let length of the cylinder is equal to L, for example. Okay, so whenever length of the cylinder is L, if you see, because of this small pressure force, so length of the cylinder is L. Okay, now if you try to calculate the drag force acting on that element, for example, you see some element like this, if you try to take the lift force acting on that, let us suppose this is the cylinder, for example, this is the surface of the cylinder, and on this cylinder you have some PS actually. Okay, so you have some PS which is acting because of some flow that's happening here. Okay, so this is d theta and this is R, so this is R d theta, this length is L, length of the cylinder is L, and this is R d theta. Okay, so you have R times d theta, this length is R d theta. Okay, now, and this is PS acting at some angle. So if you want the vertical component of this, if you resolve, PS will be something like this. So the downward component, so if you see this pressure acting on the small area dA, for example, let us suppose if this length is, if this area is dA, for example, okay, on this small area, let us suppose if this dA is PS, then this PS will give you generation of some small force dF. So dF will be normal to the surface, dF is normal to the surface, and if you take the downward component, means basically the vertical component of force, it's in the downward direction, this is dF. And what about the angle? You see here, the angle between this line and horizontal is theta, so this line and this vertical will be 90 minus theta actually. Okay, so this is dF sin theta, because dF cos 90 minus theta, dF sin theta is what you have here. Okay, so the force acting in the vertical direction, FV, dFV, force acting on vertical direction on cylinder, force acting on vertical direction on cylinder. So if you try to take this, so calculation of this lift force, for example, okay, look, before that I want to give you two mathematical points. Integral 0 to pi sin theta is equal to 0, and integral 0 to pi sin cube theta, this is also 0 actually here, sorry, 2 pi and 2 pi, integral 0 to 2 pi sin theta is 0, and integral 0 to 2 pi sin cube theta is also 0 actually here. Okay, so if you want, you can check. Normally if you do the integration minus cos theta within the limits 0 to 2 pi, so cos 2 pi, so minus of cos 2 pi is 1 and cos 0 is also 1, so that's why this is 0. Similarly here, if you take sin cube theta, for example, then in this case of sin cube theta also, if you write this as 3 sin theta minus sin 3 theta minus 3 sin cube theta in that form, you will again get this 0 expression. Okay, so integral 0 to 2 pi sin cube theta will also be 0. Okay, so these two terms are 0, just some mathematical background I am giving you. Okay, now if you see this, dFV is equal to dF sin theta. Now what is this dF? dF is in the dF sin theta, this is in the bottom direction, so this is minus dF sin theta because it's in the bottom direction, so minus dF, so dF can be written as PS into dA, so PS into dA into sin theta. So what is this value? dFV is equal to minus PS, so minus PS can be written as minus of PS can be written as this expression, P infinity plus half rho u square, P infinity plus half rho u square into 1 minus 4 sine square theta into dA. So what is dA? R d theta into L is what you have. Okay, so R d theta into L into sine theta into sine theta. So this is the expression for the small elemental force. So if you want, therefore total vertical force Fv is equal to integral 0 to 2 pi. You take the minus sign outside, for example. Okay, so you take the minus sign out minus this quantity P infinity plus half rho u infinity square into 1 minus 4 sine square theta times r d theta into L, r d theta into L times of this sine theta. Okay, so there is one sine theta. So try to understand one thing, and this, okay, fine. If you write this d theta in the last, r into L into sine theta d theta. So if you simplify this expression, you will straight away get the answer 0. Okay, why? Because if you see, p theta is constant into sine theta is there. So if you take p theta out, then you have sine theta expression here. So therefore integral 0 to 2 pi sine theta d theta is 0 plus, in this case also you will get integral 0 to 2 pi sine theta minus integral 0 to 2 pi sine cube theta d theta. Again both the terms are 0. So that's how you will observe that when you integrate this expression, you will you can integrate if you want. You can, if you, normally these are constants and this is sine square theta, integration is with respect to d theta. Okay, so if you integrate this expression, you will end up with getting a 0 lift force. Okay, so that's why in case of a stationary cylinder, you don't have any lift force that's getting generated on the body. Clear? And if you try to calculate the drag force, then definitely you can calculate, like for example, if you resolve this in this particular direction, let us suppose if the fluid is stationary and if the cylinder is moving with some velocity, then this horizontal component, if you take minus df cos theta and if you integrate, then you will get the expression which is equal to the thing that we have given you, half CD OA u infinity square is what you will get. Okay, so but anyhow, this is what I want to just give you this because in that case, at that time I told you I will show you the calculation of lift in basically the potential flows, but this is how I am going to show you actually. Clear? So we identified the expression for PS, and then through that PS we try to identify the lift force acting on the body, which is the vertical force, of course. Okay, so in case of stationary cylinder, there is no lift that actually acts on the body. Clear? So did you understand all these points about this flow past a stationary cylinder? Okay, so we started this with discussion of this combination uniform flow plus doublet. Then we have superposition theorem, then phi and psi we have identified, then we have differentiated them and we identified what are ur and u theta. Then we have seen why this can be called as streamline, means basically flow past a rotating, flow past a stationary cylinder. Then we talked about stagnation points. So we have two stagnation points, forward stagnation point and away stagnation point. Okay, then we talked about the equations by doing some coefficient of pressure analysis. Okay, and this is the thing. So finally we have identified some points where this PS and P infinity are same, or basically this coefficient of pressure is 0. These are the locations, these are the 4 locations at which, if you see, this curve is plotted with reference to P infinity. Okay, that's why these points are zeros. Okay, these are the 4 points that we talked about, and then we have seen something like this calculation of the lift force. You will end up by getting this value as 0 actually here. Okay, this r value is nothing but a, which is constant value. So you can take r out of the integration because integration is only with respect to theta. So if you perform this integration, you will see that the final answer is 0 in this case. Okay, now so this, if you summarize these points basically, so let us summarize these points in case of flow past a stationary cylinder. So summary, if you write summary, let us, because you have learned so many points, so let us write summary. Okay, first thing, obviously f of z is equal to uz plus ua square by z. Okay, and 2, radial velocity at any given location is given by u times of 1 minus a square by r square times of sine theta, sine or cos. Let us check sine theta or cos theta. We got cos theta, right? Yeah, this is cos theta. Cos theta, and u theta is minus u times of 1 plus a square by r square times this sine theta. Okay, so u times of 1 plus a square by r square sine theta. Then we have seen the case of stagnation points, 2 stagnation points, 2 stagnation points, and what are the location? At r equal to a, comma theta equal to 0, and r equal to a and theta is equal to pi. Okay, so we got the forward and rear stagnation points. So forward stagnation point and also the rear stagnation point. Okay, so this is basically the case of forward stagnation point, or this is the case of rear stagnation point. Okay, so this is the case of rear stagnation point actually. Okay, so forward stagnation point and the rear stagnation point. Okay, now also we have talked about the coefficient of pressure. So coefficient of pressure Cp, which is Ps minus P infinity by half rho u infinity square. So this is equal to 1 minus 4 sine square theta. So this is the expression. Okay, so Cp is equal to 0 at theta equal to pi by 6, 5 pi by 6, 7 pi by 6 and 11 pi by 6. Okay, so these are the points at which this is very important actually. Okay, so these are the 4 points at which you have some coefficient of pressure is actually equal to 0 in this case. Okay, and we have also observed one thing, that lift generated in case of a stationary cylinder, in case of flow over a stationary cylinder, in case of flow over a stationary cylinder is 0. Okay, so is 0. Clear? So these are some good points that we have discussed actually. Yeah, basically these are the points that we talked about. Yes, that's it. So clear? Is this clear to all of you till this, all these points, how we have identified these points based on the mathematical analysis we have done? I just want to show you this because some of you might feel difficulty in knowing these two things actually. Is this clear? Can you do this integration? Integral sine cube theta. Normally how sine cube theta integration is done actually, you know, sine 3 theta is taken as 3 sine theta minus 4 sine cube theta. Okay, so 3 sine theta minus 4 times of sine cube theta is what you take generally. Okay, and yeah, 4 sine, this is 3 sine theta minus 4 sine cube theta. So when you have sine cube theta, you write this expression as 3 sine theta minus sine 3 theta divided by 4 actually. Okay, then you will do the integration, then this term will again come out as 0. Okay, so that's what you can do. Bit of mathematics. Okay, that's it. You can do this integration. Okay, when you do this integration, you will easily get this value is 0. Okay, so this is the case of a stationary cylinder. Okay, so flow past a stationary cylinder. So these are the stream functions, velocity potential functions, okay, stagnation points, coefficient of pressure, all these things. Okay, now flow past a rotating cylinder. This is the last case, last superposition that we talk about. Look, velocities and all you can actually superimpose, but pressure you cannot superimpose in this case. Okay, means for example, you cannot add the pressure in the first case and second case equal to the net pressure. Okay, you have to apply Bernoulli's equation and you have to talk about, but velocities and all you can add because potential functions you can add directly. Okay, now if you see flow past a rotating cylinder, this is the last case in the potential flows that we discuss. Whenever a cylinder is rotating, okay, then what are the different situations? Okay, so we'll talk about that. So first of all, this is a superposition of a uniform flow, doublet and vertex. So this is combination of 3 things. Okay, whatever you have learned, all the things, uniform flow, doublet and also vertex. Okay, so please keep the heading. This is what you will see now in this case of rotating cylinders. Okay, means whenever the cylinder is rotating, whenever there is some flow on that, then what happens actually? What are the different things like velocity, pressure distribution, lift generation, all these things. Okay, so see here. So basically uniform flow, plus doublet plus vertex. Okay, so therefore f of z, you straight away calculate this f of z, the complex potential function. the complex potential function for the flow is f of z is equal to, for uniform flow, uz plus for doublet ua square by z plus vertex, for vertex it is plus minus I times of this circulation gamma actually by 2 pi times log z to the base e. Let us suppose if the this vertex, center of the vertex is at the origin. Okay, so this is the case. So this is the net complex potential function. This is expressions look little big here, you have to do little carefully, and this is the last case of this superposition of flows. Okay, after this we'll solve some numericals and that actually closes the chapter. Okay, so this, let us see this case of superposition of flows actually here. Okay, so now this is f of z. Now if you try to write the equipotential functions and the stream functions, let us see how do we write that. Okay, so this implies, so this is the case, therefore f of z is equal to uz plus ua square by z minus I times of circulation by 2 pi into log z to the base e is what you have. Okay, so this is log z to the base e. Then this is equal to u times z r into e power I theta plus ua square by z, which is r into e power minus I theta minus I times of circulation 2 pi into log, can be written as half, or generally you can write this as ln r plus I times of theta. Okay, so this is what you have, ln r plus I times of theta actually. Okay, now this we have already seen, ln r plus I times of theta, how this comes actually, log z if you write then ln of this r plus I times of theta actually, correct? We have seen that expression. So if you try to keep the real terms and imaginary terms separately, you can get u times r into cos theta plus I sin theta, plus ua square by r times of cos theta minus I sin theta minus I times of circulation by 2 pi times ln r and minus I into plus I, so total minus I square, so that gives you plus 1 actually, so plus circulation by 2 pi times theta, so circulation by 2 pi times theta. Okay, so this is what you have here. Okay, so this is the total expansion of this. Now if you segregate the real terms and imaginary terms in this, then we get real terms u r cos theta, ua square by r cos theta, and this particular expression, this expression circulation by 2 pi times theta. Okay, so if you see, this can be written as u times of, or u r plus ua square by r times cos theta plus this circulation by 2 pi times theta plus I times of imaginary part is u r sin theta minus ua square by r sin theta, so u r sin theta minus ua square by smaller sin theta. Okay, let us write this as single term, u r minus ua square by small r times sin theta minus circulation by 2 pi into ln r is what you have here. Okay, so this is the stream function actually. Okay, so this is the equipotential function whatever we have here, and this value which is here is the stream function. Okay, so this is equipotential function phi of r comma theta, and this is the stream function which is psi of r comma theta. You'll have slightly lengthy expressions, but normally these results are very useful. Okay, whatever we'll do after the derivation, whatever the results that we get, they are much important. Okay, so we have to do little carefully. So this is the expression. So the first term will be this much part, means because if you see uniform flow plus doublet is nothing but stationary case. Now additionally we introduced rotation into the flow. Okay, rotation of the cylinder. So these two terms they come excess. Okay, now let us see, if you want to look at velocities, radial and theta velocities, considering f dash of z, is equal to u r minus I times of u theta into e power minus I theta. Clear? So let us do that. F dash of z is equal to f dash of z is equal to, if you differentiate this uz plus u a square by z square, all these things, then differentiation of this quantity is u plus u a square into differentiation of 1 by z is minus 1 by z square. So u a square into minus 1 by z square minus I times circulation by 2 pi is constant minus I times circulation by 2 pi is constant into derivative of log z is 1 by z. So let us try to simplify this. So if you try to simplify this, this is equal to u minus u a square by r square into e power minus I 2 theta minus I times of circulation by 2 pi into 1 by z is r into e power minus I theta. Okay, so this is what you get. Here, if you take e power minus I theta common, because we have this e power minus I theta out, then we get u times of e power I theta minus u r a square by r square times of e power minus I theta minus I times of circulation divided by 2 pi r is what you have. So this multiplied with e power minus I theta, correct? If you take e power minus I theta common, this e power minus I theta is here. Out of these two minus I thetas, one is here and one is here. Since there is no e power I theta combination here, if you want to take minus I theta, you have to put a e power I theta multiplication. Now if you expand this in terms of cos and sine, basically if you write cos theta plus I sin theta, all these things, let us see. U times of cos theta plus I sin theta, u theta plus I sin theta minus u a square by r square times of cos theta minus I sin theta minus I times of circulation by 2 pi smaller. So this complete value into e power minus I theta. So now if you segregate the terms, this implies, or this is equal to, now take the real terms in this, out of this complete combination, take the real terms. Here you have one real term and here also you have one real term. All others are complex, correct? So u cos theta minus u a square by r square cos theta. So u minus u a square by r square cos theta. Then if you take minus I common here, so minus I times of, if you take minus I common, then minus u sin theta, this is plus u, so there is one more minus, so minus u times of, or minus u minus u, this is minus of minus is plus, so if you take this minus sign out, we have minus u a square by r square times this sin theta plus this circulation by 2 pi r. So this complete value into e power minus I theta. Therefore, if you write the radial and theta component velocities, radial velocity is equal to u times of 1 minus a square by r square cos theta, like the previous case. And what about u theta in this case? U theta is minus u times of 1 plus a square by r square sin theta plus circulation divided by this circulation divided by 2 pi smaller. So this is what you have for the real, the radial velocity component and the azimuthal velocity components. Is this clear to you? Now this is what you have here, u r and u theta. So these are the expressions. So you have to do little carefully because we have superimposed already 3 flows in it. So that's why terms come little lengthy, but calculation is not very complicated. It's very simple. The only thing is terms are lengthy. You have to write little, correctly. That's it. Okay. So the only thing that comes into difference in this part is actually this combination, circulation by 2 pi r, because we have introduced circulation to the fluid particles. Okay. So that's why if you see radial velocity remains same. Okay. Like the case. So therefore, if you write the things, we have finally per flow past a rotating cylinder, or per superposition of for superposition of uniform flow plus doublet plus vertex. We have the components something like this. So if you see, u r or generally phi of r comma theta is equal to, and psi of r comma theta equal to, because these are the important things at the end. Okay, so u r is equal to and u theta is equal to. So basically we know what is u r and u theta. U of 1 minus a square cos theta, correct, and here it is minus u times of 1 plus a square by r square sin theta plus circulation by 2 pi r is what you have here. Okay, so this is the result that we got here. So minus u times of 1 plus a square by r square sin theta plus circulation by 2 pi r. Okay, and what about these two quantities, phi and psi? So phi is u r plus u a square by r, u r plus u a square by small r into cos theta plus the circulation theta by 2 pi plus circulation theta by 2 pi. Okay, so this is what you have. Then psi of r comma theta is this minus u r minus u a square by r sin theta, u r minus u a square by small r sin theta minus circulation by 2 pi ln r minus circulation by 2 pi ln r actually here. Okay, so this is circulation by 2 pi ln r. Now plotting this equation is not very simple actually. Okay, because you actually need some tool to plot this, like MATLAB or any general plotting tools. If you have, you can plot these functions. Okay, and because this involvement of ln r sin theta, you cannot write the expression of r is equal to some function in terms of theta very easily, like we have for simple cases I have shown you, like circle, okay, and like rectangular hyperbolas, all these things I have shown you. But here this is not very simple to show you to plot. We actually need some tool, okay, to plot this equation. Now if you see, but I can show you some image from things so that you can get flow past a rotating, flow past a flow past a rotating cylinder. Okay, so flow past a rotating cylinder. So if you see images, I can show you the streamlines actually in this case. So correctly to speak, this is how you get, but of course here if you see there is some variations. Okay, so the streamlines will actually take this shape. Okay, so the shape will be something, the curve gets flatter in between. Okay, so normally if you do any, if you plot, actually you have to plot this using some tools like MATLAB or any other tool actually if you have. So this is basically some part of research paper or something, Wolfram demonstrations. Okay, fine. So if you see, this is how you get the streamline shape. So whenever this is a cylinder, if this rotation is in the clockwise sense, of course in our case we have taken rotation in the anti-clockwise sense. Okay, so this curve looks something different. Okay, so this is how the streamlines actually comes out. Okay, so that's why I'm not plotting this streamlines as of now, because they are a bit complicated here, which is much beyond the subject of this course actually. Okay, so these are the expressions. Now I will make you understand what's happening around the cylinder. Okay, because I cannot plot this streamlines, because just now you have seen they are a bit of complicated things, but I'll just show you how to, what happens on the surface of the cylinder to the fluid. Okay, and normally if you see, if you just want to see something like this, let us suppose if this is a cylinder, look at r is equal to a, what happens, you see here at r is equal to a, if you take these points at r is equal to a, okay, at r is equal to a actually here, so this is 0, at r is equal to a, u r is 0, and what about u theta? U theta is equal to minus 2u sin theta plus circulation by 2 pi a is what you will get. Okay, so the particles here have some velocity, and this velocity is also is due to this circulation, because whenever there is some circulation, because of the vortex motion, there is some flow, there is some movement of the particles in the circular paths, so that's why there is some circular motion also for the particles. Okay, now this is the cylinder. Oh, okay, now center for example, Fine. So if you see this, then this is a cylinder, okay, and this is cylinder of radius a. R is equal to a actually here, okay. So R is equal to a. Now whenever this R is equal to a, this circulation, first of all, circulation is equal to u theta into 2 pi r, which you know generally. So u theta into 2 pi r, okay. So means, let us suppose the cylinder is rotating at some velocity, then u theta into 2 pi r gives you the circulation of the cylinder. Like how strength m into 2 pi r gives the strength of the total discharge, similarly the circulation is given by this u theta into 2 pi r, okay. U theta is the velocity of any particle on this particular surface, okay. So u theta is equal to r times of omega into 2 pi r, okay. So this is the circulation generally. So now if you see, so we have this cylinder which is actually rotating, let us suppose in the anti-clockwise sense in our case, okay. Here we have taken the positive sense of rotation of the cylinder, so let us suppose this is rotating in the anti-clockwise sense, for example, okay. Then the streamlines and all is like this, as I have shown you, for example, okay. Here the cylinder is actually rotating in the clockwise sense, okay. You might have seen this. So here if you see, this is the case of two stagnation points. The two stagnation points are coming close depending upon the speed of the rotation. So the rotation actually changes here, okay. But here the sense of rotation is given in the anti-clockwise sense. But what practically happens is, the rotation can happen, means the cylinder can rotate in any directions. We are doing the analysis for the anti-clockwise sense, okay. So when you do analysis for the anti-clockwise sense, okay, if you want to draw the streamlines, I'll make an attempt to draw. Okay, and the flow here gets some stagnation points, which I will show you. This stagnation points will be in such a way that, because the fluid is trying to move in this direction, the cylinder will try to oppose the flow. So obviously there comes some stagnation at some location, and these two angles, if you see, there is some relation between those two angles. The sum of those two angles is equal to 180 degrees. We'll see in the next step how they are coming. But if you just want to try to plot the streamlines, they come something like this flat, and then they go like this, okay. So this is how the streamlines actually comes out, okay. These are nothing but the plots of this function, which is involving some ln r, all these things, okay. So this is how you have the things, and these are the stagnation points generally, okay. We'll see how the stagnation points and all can be talked about, okay. So these are stagnation points in the flow. Stagnation points in the flow, okay. Now if you see, first stagnation point, so first of all let us start the analysis with stagnation point. Stagnation points, okay. So at stagnation point, magnitude of velocity is actually 0, and this implies ur is equal to 0 and u theta is also equal to 0 in this case, okay. So ur is 0 and u theta is also 0 in this case, okay. So whenever ur and u theta both are zeros, so at r is equal to a, ur is 0 anyhow, okay. Now at r is equal to a, u theta is also should be 0, okay, on the top of the cylinder. So this implies, what is the meaning of u theta equal to 0? This expression u theta, this expression, or basically this expression is actually 0, correct, at r is equal to a. So minus 2u times sine theta plus circulation by 2 pi r a, circulation by 2 pi a, this should be equal to 0 actually here, okay. So this has to be 0. So this implies, what about your sine theta? Means basically, the radius is at the surface of the cylinder. So at what angles you have the stagnation points? This is what you need to understand. So therefore, from this equation, we have circulation, or 2u sine theta is equal to circulation by 2 pi a, circulation by 2 pi a, and this implies your sine theta is equal to circulation divided by 4 pi ua is what you'll get, okay. So circulation divided by 4 pi ua is what you have here, okay. So this is the expression for theta where you have the circulation. Okay, so first stagnation points, try to understand this. First stagnation points, your sin theta should be equal to circulation divided by 4 pi u times of a actually here. Now obviously all these are some values, so this is a positive value, a is length of the cylinder, all these things you have, so sin theta is something that you have. So if you see one thing, obviously this is a positive value and sin theta cannot move beyond 1, so therefore because all these values involved here are positive, we have taken the circulation in the anti-clockwise sense which is positive. Okay, so therefore 0 less than sin theta is less than 1 actually here in this case. Okay, so 0 less than sin theta should be less than 1 actually. Okay, because whatever is this value you take, that value is always positive, so and maximum value of sin theta can be only 1, so that's why this circulation can lie only between 0 and 1. Okay, 0 less than circulation by 4 pi u a, this quantity is less than 1 actually. Now try to understand one thing, when you calculate this value, means for example if I give you some values that circulation is this much, okay, radius of the cylinder is this much, okay, velocity of the flow is u some 20 meters per second, let us suppose if I give you, you will get some value here, correct? So therefore whenever sin theta is equal to some value, there will some positive value actually, there exist two values of theta, like for example if sin theta is equal to, let us suppose this value got 1 by 2, okay, then sin theta equal to 1 by 2 happens at theta equal to 30 degrees and also at 150 degrees, so sum of these two angles is actually 180 degrees, yes or no? So therefore two values of theta satisfy the above equation, two values of theta satisfy the above equation, such that theta 1 plus theta 2 is equal to 180 degrees, yes or no? Obviously for sin theta is same as sin pi minus theta, so obviously sum of those two angles should be equal to 180 degrees actually. Okay, so here if you observe, that's why you have two stagnation points in such a way that if for example this angle is theta, then this angle is also theta. Okay, means if for example this angle is theta, then this angle is also theta again. Okay, so that's how you have two stagnation points. Now I want to ask you one thing here. Look, let us suppose if I give you a cylinder for which a radius of the cylinder is fixed, so a is a fixed value, and let us suppose there is some flow which is coming at some velocity 20 meters per second something, let us say, so it has some fixed value, but one thing that I can change is the speed of the cylinder, correct? Means let us suppose initially the aircraft engine just started, it revolves slowly, then slowly it gains speed, diameter of the cylinder is same, the velocity intake is same, but the rotational speed is increasing. So in such case what happens, let us suppose if this circulation increases, for example, okay, look, if circulation increases, if circulation of cylinder increases, for example this implies circulation by 4 pi ua also increases, correct? So this quantity also increases actually, circulation of 4 pi ua also increases. Now tell me one thing, whenever sin theta is equal to, this implies theta value or theta, look for example this is 0.5, let us suppose because of increase of circulation this went to 0.8 for example. Okay, so when this is 0.5 you have some value of theta. Now let us suppose if this is 0.8 for example, then in such case theta also increases, correct? So theta also increases, okay, so when theta also increases, look what happens. Look, I will ask you one thing, so try to understand this. There is a circle, normally you have the stagnation points in such a way that the stagnation points are here on the same horizontal level, such that if this is theta, then this is also theta basically. Okay, so this is theta, then this is also theta, so that the sum of these two angles is actually 180 actually. Okay, so this is theta and this is total 180 minus theta, so sum is 180. Now as theta increases, what happens? This point will go to some higher angle, correct? So this angle will be theta dash, for example. Okay, so in this case, let us suppose this angle is, after increasing circulation, this is theta dash. Now definitely 180 minus theta dash will also come somewhere here, yes or no? Means basically if you see, now this angle will also be theta dash. One thing you have observed here, when theta is increasing, theta also increases. If you see the distance between stagnation points, whenever the rotation speed of the cylinder is increasing, so whenever the rotation of this cylinder is increasing, if circulation is increasing, then the stagnation points will come close, yes or no? Yes, this is 100% clear. So theta also increases, and this implies stagnation points move close to each other. Stagnation points move close to each other. Stagnation points move close to each other. So whenever stagnation points are moving close to each other, then definitely there comes one situation where both the one particular speed of rotation, where normally it has two stagnation points. Okay, so it has two values of theta, therefore there exist two stagnation points generally. Two stagnation points in general. But try to understand one thing, whenever the rotational speed is increasing and if this stagnation points are coming close to each other, then there exists one particular situation where these two stagnation points will meet each other at this 90 degrees, yes or no? Means as theta increases, there comes a location where at theta equal to 90, of course at theta equal to 90, these two stagnation points will come close and finally they will meet actually at this location. There comes a situation like this, yes or no? So as theta increases, as circulation increases, stagnation points move close to each other. So therefore when this rotational speed keep on increasing, there comes one particular situation where this stagnation points will actually meet, and instead of having two stagnation points, you will have only one stagnation point in that case, correct? So therefore in such case, if you see, as theta increases or as circulation increases, stagnation points come close to each other. Stagnation points come close to each other. Okay, so when they come close to each other, then therefore there exists a condition in the flow where both the stagnation points meet, where both the stagnation points meet and the flow experiences a single stagnation point in that case. Okay, a single stagnation point, and that comes out at theta equal to pi by 2. We know that, okay, because you see whenever this increases, if both the stagnation points has to meet, then this angle of theta has to be 90 degrees, correct? So therefore for single stagnation point, for the case of single stagnation point, theta should be 90 degrees. We know this. So this implies sin theta should be equal to 1. So what's the meaning of sin theta equal to 1? Circulation should be equal to 4 pi UA actually here. Okay, so circulation should be equal to 4 pi UA. Now what is circulation? We know circulation is actually equal to u theta, means the top velocity of the velocity of the particles on the surface of the cylinder into 2 pi r, and r is nothing but a in this case. So this is the value of circulation, u theta into 2 pi a. So this is equal to 4 pi u times of a actually here. So if you simplify some result, pi gets cancelled, 2a can cancel this a, and this is 2. This implies your u theta should be equal to 2 times of phase stream velocity. This condition is very important condition. This condition is asked generally in almost all exams where potential flow is there. Okay, not in GATE of course, but in all the other state level exams or many other like SSC, JEE, all this kind of things, this question came many times. Okay, so the phase stream velocity, I told you, results are very important. Okay, this is one of the very important result again. So whenever the peripheral velocity on the top of the cylinder, and what is u theta? U theta is equal to r times of omega, which is a times of omega here in this case, which is a times of 2 pi n by 60. So this is u theta in this case of rotating cylinder. Okay, so u theta is equal to a into 2 pi n by 60. So this u theta, the peripheral velocity on the cylinder, is equal to, should be equal to 2 times of the phase stream velocity for the both stagnation points to merge, and you can see only a single stagnation point. Clear? So this u theta is equal to 2 times of u is the condition for the case of a single stagnation point. This analysis is very important for you. Clear? Okay, so this is the case that we deal with generally, single stagnation point case. Normally, like in here, like in case of Rankine half body, you told that there exists only single stagnation point. In case of flow past a stationary cylinder, you told there are 2 stagnation points. But here in case of a rotating cylinder, you cannot decide on the number of stagnation point. It depends on the rotational speed actually. Okay, so if the rotational speed is in such a way that this condition is getting satisfied, you will experience only 1 stagnation point in the flow, and that too, that stagnation point will be this somewhere here means very close to this, at theta r equal to a and theta equal to this close location, you will experience a stagnation point. Okay, like basically the case here, this stagnation point will be just on the top of the cylinder. Okay, but if the circulation speed is something different, then you have 2 stagnation points. Okay, that's why number of stagnation points in this case is not a fixed quantity. It can be 1, it can be single stagnation point, or it can also be 2 stagnation points. Clear? Circulation is basically the measure of rotation, that's it. Okay, like for example inertia, mass, if you take mass, if you want to define mass is the measure of inertia. Similarly, circulation is the measure of rotation of the fluid particles. Mathematically we have seen what is its integral v bar dot dl bar, all these things. Okay, so there is one last concept which is the lift generated in this case. Okay, there is something called Magnus effect, but I think time is short actually, we have only 1-2 minutes, so we will deal that in the next lecture. Okay, so calculation of lift force and what is Magnus effect we will see in this case. Okay, so that Magnus effect we will see. So these are the things that we discussed in today's session, a bit of mathematical session, but still it's a good, there are some good points to understand here in this case. Okay, so we talked about the flow past a stationary cylinder, superposition of uniform flow and doublet, and then we have seen the pressure variations, all these things, then calculation of the area, everything here, and finally this flow past some rotating cylinders. Okay, so we identified these things. Okay, so we'll stop here for now, and we will go forward in the next session. Okay, we'll calculate the lift forces, and we'll see what is the lift force actually. Okay, we'll see that. So then please join back at 9:30. Okay, we'll continue the discussion. Thank you all. Thank you.